Principal component analysis breaks down the dataset in terms of its principal components. In this video, we will go through the mathematical representation of these principal components and how to represent the data in terms of those principal components. These principal components are represented mathematically as vectors in the feature space. Each principal component is represented by a direction of spread or variance denoted by the vector u. These vectors are unit vectors, so their length is equal to 1, and a scalar value lambda that corresponds to each direction u. This is the variance of the data along that direction. In our dataset here, the red diagonal line is the first and major principal component, which can be broken down into the diagonal direction u1, and its length will be related to the lambda value, which is the variance of the data on the diagonal direction. The same applies for principal component 2. It has the direction of u2 and the length of lambda 2 relative to the spread along the u2 direction. Because we only have two features in the original space, we expect two principal components in the PCA space. This is due to the fact that the principal components are the rotated version of the original axis. This rotation is to align the axis with the variance of the data. That way, the horizontal axis always contains the maximum variance of the data, and the orthogonal direction contains the remaining variance of the data. This is in case of having only two features in the original space. Of course, this can be generalized to a space of n features. In that case, we expect to get n principal components with their corresponding directional vector u's with n elements. That is because the direction vector is now represented in an n feature space. We need x, y till n features to know its location. And for each principal component, we have the variance that is explained by the corresponding lambda. Note that the lambdas or variances along each direction are always ordered in descending order. That means PC1 contains more variance, so more information about the data than PC2. That means that PC1 is more important than PC2. For mathematical convenience, we can place all the u directional vector in one matrix. The column of this matrix are the individual u vectors ordered in descending order of their corresponding lambdas or variance spread. We would now like to represent the data in terms of its building blocks. We want to represent the data using the PC feature space instead of the XY feature space. To do so, we need to project the data points from the original space to the direction of the principal components using these equations. The new x-coordinate or xPCA is the dot product between the data point location xy by the PC1 unit direction vector u1. That will result in one single number, which is the new x location relative to the PC1 direction as the new horizontal axis. The same goes for the new y-coordinate or yPCA. It is the projection of the location in the original space into the u2 unit vector. We can also use matrix multiplication to do such transformation. That is the exact same equations as above but in matrix form. We can easily see that the points in the PCA space are a linear combination of the original feature space. The xPCA features depends on both the original features x and y, or coffee and milk in our example. Now xPCA represents something like this. All cups of coffee that are on the xPCA axis, those are all points that are along the red diagonal line in the original feature space, all have the same recipe of coffee. of U11 amount of coffee and U21 capsules of milk. If we now plot the data points after projection on the PCA space, we can see clearly that the data is still of the same shape and structure. All data points are just rotated such that the principal components are now the new features of the data. And that is what PCA is seeking in the description step. It finds a better perspective to look at the data while keeping the structure as is. Using this representation, the maximum variance is along the horizontal direction, and the orthogonal direction of PC2 now has the minimum variance of the data. Also, what we got as a plus from describing the data using PC1 and PC2 is that the covariance between PC1 and PC2 is 0. Therefore, PC1 is totally independent of PC2. Here we also show the generalized way to project n-dimensional data with m data points on the principal components. In that case, PCA will find n principal components, so n columns in the U matrix. Then we can project the data into the PCA space by matrix multiplication. X original is the data matrix where each row is a single data point. The output data matrix X PCA is a rotated version of the original data matrix. But the question is, how can we find these principal components mathematically so we can project the data onto them? This is done by eigenvalue decomposition of the covariance matrix of the data. The eigen decomposition of n dimensions data covariance matrix returns n eigenpairs. Each eigenpair is an eigenvalue with its corresponding eigenvector. Those eigenvectors are unit vectors. They encode the principal component unit direction. So U1 till UN direction vectors. And its eigenvalue are the variances along the principal directions. So our lambdas, lambda 1 till lambda n. PCA will always make sure that the eigenpairs are ordered in descending order of their eigenvalues. Since we now have our unit vectors ordered in the right order, we can project the data on the PCA space as discussed earlier in this video. In this video, we went through how to get the principal components mathematically using eigenvalue decomposition. We also discussed how to project the data points onto the principal directions or eigenvectors of the data.